those that survive first part of the talk, I will stop 5:15 sharp. Doesn't matter what. So just half of this. Okay, so let me talk a little bit about time consistency, what it means. And there's a strange things about that also happen. Time consistency was discussed in this type of a long time. And now, with this development of this nested risk measures, it's again, there's a lot of talk about that. There's no general agreement what time consistency means exactly, so far, as far as I know. There's no general agreement to that. And because of this, and I'll try to show you some very strange things that really might happen. And basically, there are two approaches to this, which were at least considered recently. Again, going a long way back. And one approach is, from the point of view of risk measures, one considers some type of properties of risk measures. All right? The other approach, which also go probably originally to this Bellman, and which credited to inventing dynamical programming, is to optimal solution. So from the point of view of this Bellman, and let me see. Oh, this is a quotation, famous quotation from him. Remember, it's going a long way back. What it means that we, at the beginning of this, before we observed any data, we made optimal decision. What is optimal decision? We decided about optimal policy in some sense. Right? We have objective function. In risk neutral case will be expected value. And suppose we can solve that. And we have an optimal decision. It can be more than one optimal decision for the problem. It can happen there's no optimal solution at all. But suppose there's an optimal solution. We decided about that. Then you see what is written. This is optimal policy. No, it's a start to initial condition start, right? And then we're halfway through. We have 10 stages, and we're now at day 5. We have 10, we decided optimize it for 10 days. We're now day 5. We observed what happened before. We know the history. And then we look in the future. All right? The question is, the policy that we design at the beginning, before observed any data, is it still optimal? Okay? This is what is written here. It's supposed to be optimal. Now, what is written here is not clear. Why? Because if I want to look at this from this point of view, I have to say what is optimal at day 5. Right? Optimal on what I observed, on conditional what I observed so far, looking in the future. When I have this, when I look at this, if I take expected value, there is a very natural answer to that. I looked at the conditional expectation. You see, it's all about this conditioning type of thing. I make decision, conditional what I observed so far, I know the past, and for the future, I assume only that I know the distribution of that. I don't know the future, but I assume that I know distribution of that. So I'm a certain node of the tree. If you know what is scenario tree, it's what can happen, the state of nature that can happen. I put on that conditional probabilities of moving from one node to another. I have the stochastic process in some sense. I'm certain node of the tree. This is this situation now. I see the past, how I got there. Conditional on that, I have to decide what my optimality for the future. Because I say, OK, I will not recompute my optimal policy. I do not change that. It's all about optimality, what optimality means. in the classical case, it's just conditional expectation. I still look conditional expectation, it's very natural. If I start to look at more general, it's not clear at all what is my definition. If I decided what optimality at the beginning of the process, I didn't tell to the user what is optimality after that. I have to say it. Okay? So, I have to formalize this type of thing. Okay? And this is one natural way of doing that. Okay? So, this is a problem here. This is what I already talked about. Even, for example, if I take average value at risk as a total of the total sum of the total cost, it's not the same if I write it in a nested form. Okay? Now, so, and it's possible to give some strange examples. And really what is interesting that when we started to talk about that, some of the formulation that people did and put in a computer were strange. There was something wrong about that. Right? It was not clear immediately, obviously, what is wrong about that. It looks very natural thing, right, that we have here, that when I look at the optimal, when I look at the future, my optimal criteria, my objective function, should not depend on something that already I know what cannot already happen because I already observed part of the tree. I know that certain things already cannot happen, which I look at the beginning. Some formulation do not satisfy this simple principle, already started strange. Right? Now, this is exactly what I said. Right? In very abstract form, imagine that we have the process, right, of random outcomes, and T, capital T here, is a total horizon. We only talk about a finite horizon of that. And this is small t is where I'm now. And this is the tail of my process. So one thing, if I look at this, if I try to minimize the total sum of this, it's very natural to define optimality by conditional expectation, what I observed so far. So I can try to do the same for average value at risk, right? Here I put at 0, this corresponds to that, it's the same. But if I'll try to do the same thing here, it will be not the same as when I optimize that from the beginning, this one. Because it doesn't have this decomposability property. It's not the same. And there's a problem. So it looks natural, right? That what I look here, okay, I will define, for example, if I look at the coherent risk measures, low invariant, you have conditional analog, and I look conditional what I observed so far, I take a corresponding nested form of that, similar to conditional expectation. Right? In other words, I look at the nest from the beginning, I try to minimize it in nested form. If I do it like that, I can take, for example, nested var or something else. Right? Then it looks natural. What will be my optimality, conditional what I observed so far, looking in the future. Right? It looks. What is very surprising is that even if I have this nested form, it does not ensure this optimality of certain policies in that sense. Very surprising, right? For example, if I take average value at risk. Reason for that, let me show some positive results. Okay, this is exactly what I'm saying, right? That if I look at this certain point, it still should be optimal. I don't have to recalculate it. And for that, I have to make clear statement. What is my optimality or conditional on what I observed so far. Otherwise, it doesn't make sense. Okay? And then I have a big choice how to do that, how to decide what is a conditional optimality is. So if I have nested form that I wrote it, at least it looks natural. Okay? And then what people in finance, what the people look at this, I can talk about properties of this type of this conditional monotone, this multi-stage, multi-period rather, risk, these measures, okay? And one of this approach that people took in financial engineering defines certain properties of that. And there are some natural properties, right, of certain type of monotonicity of that. And then some additional properties, I don't, there's some results. Basically, it's possible to show that if one assumes a certain type of properties here, which is very natural, necessarily what you get nested formulation of that. This final result due to Andrzej is not here, Roginski. He showed that if I have some simple axioms of that, very natural, necessarily it leads to nested formulation of that, right? It's the only way how I can have these properties of this risk, if I define this very natural properties risk measures, how they be this consistent in that way. The consistency here is again in terms of objective value, in terms of the optimization criteria. So natural question to ask how it's related to optimality, this consistency, time consistency, optimal solution. And there's some surprising things here. Right? Okay. This is exactly this property that I talked about. That this is appeared in several this formulation of that. Right? This property of this risk measures, which is plus some additional natural thing, lead the nested formulation of that. I wrote it here. This is additional property. This usually satisfies these coherent risk measures. It's all. Now, what happens is very interesting. It's possible to show that if we have this type of decomposability, if we have this type of property, and the optimal solution is unique, there's only one optimal solution of my property, of my problem from the beginning. It will satisfy this time consistency in sets of Bellman. But it's not true anymore if we have multiple solutions. And the reason for that is the following. Remember that when we talked about coherent risk measures, we have monotonicity property. Right? No, I hope you remember that. So maybe I should go back. But monotonicity means that if I have two random variables, one is always greater than or equal than the other, then the risk of one is greater than or equal than the other. Right? Monotonicity, it's monotone, non-decreasing. But average value at risk, for example, is not strictly monotone. What it means is that you have one realization which is strictly bigger than the other. In other words, on some positive measure, one is really bigger than the other. Right? Then it's natural. Then risk measure of one should be strictly bigger than the other. Greater than, not equal, greater than. Average value at risk doesn't satisfy this property. Maximum doesn't satisfy this property. It's very clear. You have certain sequence of numbers, finite numbers. You take maximum of that. You change one, which is not maximum. It doesn't change the maximum. Right? Similar thing happens with average value at risk. Because of that, and it happens when, and this is very strange, at least it was very strange for me, is that one has many optimal solutions, and that happens very easily. One can give easily examples of that. Even if I have this decomposability property, right, then it does not enforce, right, that this optimal solution will be conditionally optimal. There exist some policies which are optimal in the beginning, even for nested AVAR, right, which are not optimal as we go on. Very strange thing, right? So because of all this, what one exactly understand by time consistency, how exactly it's not something simple which one can, and there's no general agreement on that, okay? This is probably, I probably will, I don't want to talk more about this. It's not this trivial thing. And it's possible to construct such example, like such very simple examples exist of that type. Now, maybe I should say a few words about possible solutions of all of that. Right? Numerical solution. It's big, this big, very big question about that. Okay. When we talk about that, the only way how I know how one can approach that is try to solve dynamical equations. There's a strong indications, mathematical, empirical, that generically multi-stage stochastic programming are intractable, not possible to solve, the way this was formulated. Right? The reason why it is, even approximately, even by randomization method. Why? Because, okay, if I will try to look at that from the point of view of number of scenarios, try to approximate this tree, number of scenarios grow exponentially. Very quickly, right, one cannot put it in a computer in any reasonable way. So in terms of, so because of that, in terms of scenarios, in multi-stage case, it's basically hopeless. And in order to approximate the corresponding process, we have the corresponding process, we need branch our tree at every stage. So at every, in the beginning, I have to discretize my distribution, say 100 points, not that many. Right? Conditional on that, I have again generate 100 points. Conditional on that, I have to multiply that. So even if we have 100 points per stage, even if I assume independence, the total number of scenarios very quickly become astronomical. So if I look at the linear programming, theoretically, I can write it as one large linear programming problem. But it will be so huge that there's absolutely no way how I can even put in a computer, or how I can solve that. Right? So, by the way, you probably heard a lot about robust optimization, okay? Which is in some sense easier, because in robust optimization, it started with linear programming. It's much easier to specify uncertainty set, the whole distribution. It's easier to solve. And there's an analog of robust optimization for multi-stage. It's called adjustable robust optimization due to Nemirovsky. The same problem. It's computation generically, it's computationally intractable. Right? It's also possible with some standard dynamical equation to do some other things, but it's much easier to understand. It's probably still easier to solve, but in general, there's no way. It's not a theorem, but there's a strong indications that this is the case. Now, by saying that, I don't want to say that we can completely forget about multi-stage programming. It's too important. You know that in integer programming, combinatorial optimization, I know that most problems are intractable, NP hat, whatever. But it didn't stop the people trying to solve that. So some things probably could be done, and some things could be probably solved. So one of the large class of this type of that, trying to solve dynamical equation. What is a dynamical equation? Dynamical equation is optimality conditions. And by writing dynamical equation, in principle, I reduce infinite dimensional problem to finite dimensional. The problem with dynamical equations, even if in disk neutral case, even if I assume the stage-wise independence is how I compute the cost-to-go functions. Right? Actually, there are several problems with it. The largest of one problem is how we compute expectation. No? This we can, to some extent, we can deal with it by using Monte Carlo and all that. But the largest problem is how can I keep in the computer, how can I describe in the computer high-dimensional function? If I have one dimension, right, function of one dimension, of one variable, I can discretize its range, and it can get a reasonably accurate approximation of that. If I have two variables, and suppose I need 100 points for that. I have interval, I discretize that, I will remember the points that give reasonably accurate estimate. If I have two dimensions, I will have 100 by 100. I can put every point there, because I need somehow uniform way of approximating this function. If I have 4 dimensions, it's already out of question. Right? So one probably can push it 2 dimensions, maybe 3, but already at 4, it's one start forget about that. So one of the way how this way people try to do so deal with that, some sense approximating the cost-to-go function. And this, for what I showed you, this stage-wise independence is crucial, because then the cost-to-go function only depends on state variables. Somebody already asked me about that. In many cases, stage-wise independence is not realistic. One can deal with, to some extent, this by Markov type of property, and that it's a long story. Still, if I have 100 dimensions, the state number state here, variables, is 100, how I approximate? In linear, when you have linear program, this cost-to-go function or value function are convex. It's very important. So I can, when I do that, and this is what people do in deterministic optimization when they solve convex problem, I can try to approximate it by adding cutting plane or supporting planes of that. In convex case, I can supposedly I can compute subgradient or gradient that, I add support of that, and eventually I have better and better approximation of that. Now, what is the problem with that? When I deal with deterministic case, just one, I don't need to approximate my function well everywhere. In the beginning, probably very crude way of approximation, I can move, I can make improvement. As I approach the minimum, you can think, I cannot write it, but you can see this minimum, I need to make more and more accurate approximation near the optimal. In stochastic case, it's not true anymore, because when I look at these cost-to-go functions, I don't know where I hit it, because it will depend on particular realization of corresponding optimal. So ideally, I need to have better and better approximation of that uniformly. And this is disaster. Because when if I want to approximate my cost-to-go function by piecewise linear function, take the maximum of these cuts, if I want to approximate it uniform way, number of the cuts that I need grow exponentially. So already if I have, say, 10 dimensions, it become out of questions numerically, right? So nevertheless, one can try to solve this numerically. Maybe I don't need to approximate my cost-to-go function everywhere uniformly. Maybe there's really important regions okay? When I should reasonably well approximate that, it should be not uniform. And this is the idea of this algorithm, right? Of that, which became very popular. This original paper is, you can see that, which was developed here, right? And it goes, the idea is going backward and forward. When we go backward, we have cost-to-go function. We assume independence of stage-wise independence. Even if it is not like that, this evidence type Markovian property one reduced to this case. There are tricks how one can do that. Okay? And one compute more and more cutting planes solving dual problem. Dual problem give a certain subgradient and what add this cutting to that, going backward all the way. If I have 120 stages, for each one of them I add cutting planes, and I have to put it computer memory. When I go the forward type of algorithm, it's randomly generated the sample path, one sample path. And when I have current approximation of that lower type of approximation, I solve, going forward, solve the corresponding linear programming problem, and I add these points where I add cut afterwards. And this is very essential that I do it this type of conditional type of that, okay? So going forward and backward, I approximate my cost-to-go function better and better, right? And theoretically, it's possible to show that it converges under some conditions. And it's possible statistically to construct the upper bound and lower bound, and one can see the gap of that, okay? Now, one should understand, probably I should say it here, that the fact that it converges intuitively is quite obvious. Why it's obvious? Because we approximate cost-to-go function better and better. What is surprising that to prove it mathematically is quite technically challenging. But nevertheless, the fact itself that we prove its convergence, one should clearly understand, doesn't give any guarantees. Because this doesn't give any guarantee that we solve the problem with reasonable accuracy in reasonable computational time. Okay, now, this is this type of algorithm. And this methodology was developed now that one can estimate the error. They say the several procedure that one start with continuous distribution. One discretize this continuous distribution in a certain way. Right? Then one solve this problem with certain accuracy. And it's also possible to evaluate the error of the solution for original continuous distribution. It's all documented. If one if somebody interested, I can forward you all these reports and papers on that and so on. You see? So again, the first idea of that, the cost-to-go functions only depend on the state variables, not on the past data. And we approximate it by piecewise linear. And this, we have the statistical property that in principle, one can construct a statistical bounds for the true, also for the true problem. And what is important is in that way that when we approximate the cost-to-go functions, they also, it generate the policy for the what so-called true continuous problem before discretization. Because I can go forward, and every time I solve linear programming and generate a policy. Okay. Now, this is what basically I said. It's possible, this is for risk-neutral case. It's possible to extend it with additional effort, not that large, to also risk-averse case. Okay? This is stopping criteria. I will not talk about that. This is typical example of this type of algorithm. Say for risk neutral case, we have low bound, right, which is improved all the time, but as we add more and more cards, monotonical improvement. You see that after many iterations, it starts to stabilize. In other words, it doesn't improve anymore. Okay, and then we have the upper bound, the statistical one. When we go forward, right, it's random, and there's you can see this. There's some type of random noise here. One can smooth it out, and statistically, one can see what the gap of the solution. It gives you estimation of the gap. Let me show you some example. So, from theoretical point of view, the important, very important question, which is not clearly understood in that type of things, is rate of convergence. It's not enough to prove that it converges, right? But if it will converge in billions of years, I will not live long enough to see that. So the important question to understand how fast the rate of convergence, and some available results of that type are quite pessimistic. Basically, the conjecture is that the convergence is, the rate is become bad as with number of state variables increase, but number of the stages is not that important in this type of grid. But what is very important, number of state variables. And it's understandable because Costigo functions become bigger and bigger, how you approximate them. Now this is example of this what was solved this by this problem. And you can see this, oh, by the way, it's possible to do that with this using the average, this say, risk measures. The additional effort by solving it by risk measures is not large. It's only question how one computes subgradients, and there's formulas of that. So it's also possible to, and this was implemented with this type of risk measures. Okay, you still have, they still have equations. One can write it all. That's what I said. There's a possible to write formulas how to compute the subgradients. It's not that difficult. Otherwise, it's basically the same type of. So let me show you some examples. Okay, this is what was solved for problem with 4 state variables, just 4. Right? With this depends on initial conditions. You know, if this for how much water we'll have in the beginning, low. This was low, and there's a lot of that. And you can see after a while it stabilizes. They start to forget about the initial condition. About here, it start to become stationary. This is a quantiles of that. This quantiles is a peaks. Right? What can happen with, say, suddenly cost is become much bigger than the average for risk neutral case. So the whole point of this risk neutral was to smooth out this type of quantiles at every stage of the process, every month. It's also possible to see, right, how much variability of that with respect to discretization. Discretization was done by randomly sampling that. And this variability, in other words, one generates sample per stage, say 100. Total number of scenarios is still astronomical, 10 to the power 200. 10 to the power 200 you cannot put in a computer, right? But it still was possible to do something. And what it was surprisingly maybe the variability with respect to the sampling of the sample average was quite small. You can see it here. One of the possible explanations of that is that we also average over time here, right? Not over this stage. But anyway, these were results. And this is what is the risk, what is the intuition behind risk-averse approach here? Okay. Ideally, one of the possible approach, I can try to write chance constraint for every stage. In other words, I can say every stage, conditional what I observe, this cost should not be bigger than certain number, and put that in the constraints. I can do that, try to do that. If I'll try to do that, I can face infeasibility of the problem, because it's not possible to ensure that this cost will not go up above certain level for any possible realization of the data process. So then naturally I say, okay, I cannot do that, but at least I want to control it with certain probability. The probability it will be bigger than certain number should be small. And I put that in a constraint in every stage. Right? I have to enforce conditional, but theoretically it's possible to do. Still, it could be infeasible. Still, I cannot enforce that. It's one problem. Another problem, if I look at the chance constraint, it's very difficult to solve, even for simple static problem, not talking about multi-stage. So I can do it with average value at risk. Instead of value at risk, I look at average value at risk and put it in a constraint. Okay? If I do that, at least it's convex. It's much easier and conditional form. But yet I can face infeasibility. And when we face infeasibility here, you may know even when you solve that, it may happen you will never see that. Why? Because you remember the original was continuous. And we discretize that. No, here we discretize by random sample. For random sample, for discretized problem, I solved it to optimality, to feasibility. But something else happened in reality. And my solution, which was feasible for discretized problem, suddenly infeasible. Infeasible, it's useless. Because for that, I cannot even implement that. It's not that I lost 5% efficiency or something like that. It's much worse. So by doing that, putting that in the constraints, I have no guarantee of feasibility. And the worse, by solving that, I even will not know that. Because of that, this idea, this is what we talked about, that we put that into objective function as a penalty. This is justification what I was telling from the beginning. One can argue about that, it's still, but at least it's reasonable formulation of that from this point of view. And of course, the question how to choose these parameters, which is not a simple question, but at least here I don't have at least this problem of infeasibility. And then we have this formulation that we talk about that, and this all that we discussed that, the same type of algorithms, and then we have this corresponding dynamical equations. We can discretize that, compute the subgradients, supporting planes. It's very similar. In fact, the additional effort that is going that is not that large compared to that. Okay. This is probably last thing that I show. Okay. No, I'm almost on time. Okay. So this is a last example of the typical type of example. You can see here, this is risk. This is black, is risk neutral solution, and this is risk averse. These are quantiles, the peaks of that. On average, there is some loss, of course, when I impose this type of that, but you can see that it moves significantly this higher peaks, higher costs of that. So this is one of the typical examples of that. Okay, I think I'll finish by this. Oh, actually, a few minutes even before. I got tired.
Now we have time for